It's my honor to introduce the plenary speaker, Alexei Borodin. Professor Borodin is the Barton Weller Professor of Mathematics at MIT. He has a PhD from the University of Pennsylvania, which some people in my family are very proud about. Before going to MIT, he worked at the Institute for Advanced Study at Caltech. He's been at MIT since 2010. He has won a number of prizes, including the European Math Society Prize. He's been a speaker at the ICM. He won the Levy Prize, the Poincaré Prize, and he is a fellow of the Bernoulli Prize, and is a fellow of the American Academy. And the Fermat Prize, I forgot that. He will speak to us on the geometry of dimer models.
Thank you very much. Thank you very much for a very flattering introduction. Thank you very much for the invitation. I'm delighted to speak here. So the topic of my talk is geometry of dimer models, and in general, things that I enjoy in mathematics are the ones where the problem is very easy to formulate, but somehow understanding what's happening with it requires a certain depth of mathematics. And so I will try to show you an example of such. So dimer models is really a term that came from physics. So a dimer, one starts with a finite graph, as you see on top. And so a dimer is just an edge. So you see some edges are circled in red, so these are dimers. You can think of a molecule that has two atoms. That's the original, the origin of the word. And then the dimer covering is when these dimers cover your graph completely. Not every graph can be covered, but we'll consider only those that can be covered. So every vertex gets covered exactly once, right? And then what we'll be interested in is what a random dimer cover looks like. So one starts with the graph. There will be some number of dimer coverings, and we take them uniformly at random, pick one, and we want to say something meaningful about it. Okay, so that's the overall setup. So the dimer models first appeared in chemistry literature in the 1930s, where they really thought of dimers as of molecules. They were extensively studied by statistical physicists in the 60s because of their relationships to the Ising model. So that was, or that is the famous model of ferromagnetism, and in 2 dimensions it was famously solved by Onsager in the 40s. And in the 60s, it was realized that there is an approach to it using dimer models, and so that's when they became popular. Then there was a pause, and then in the 80s, another group of physicists picked dimer models up, and that is actually related to the pictures that you see on the right. So what are these pictures of? These are actually photographs from one of the physics papers. What you see is a droplet of helium at a very low temperature. So the top picture, I'm not sure if the text is readable, the top picture is at about 1.4 degrees Kelvin, so above the absolute zero. And then as one drops the temperature, you see that the droplet starts to freeze and it starts to develop facets. It's first round, and then there was one facet appearing, and then the temperature goes down, there are more facets, and then eventually it becomes a crystal. Right? So it's unclear why, or at least it should be unclear, if you see it for the first time, why these pictures have any relations to the dimer covers. But hopefully, as the talk progresses, we'll see some relation. And then mathematicians, as usual, relate to the show. To the extent that I meet physicists who look at me and say, can you tell me why mathematicians are still looking at dimers? And I have an answer. Well, I did give some answer to you, and I hope I might come back to it at the end of the talk, and I'll say what I meant. But I do think that we found things that physicists, well, maybe they didn't care. But some of them do care now, actually. Right. OK. Maybe one terminological remark is that dimer cover in mathematics and combinatorics is usually called a perfect matching. But I will deliberately stay away from that terminology because dimers is a more convenient language in this point. So I will look at only one type of graphs, which will be domains in the square lattice. Okay, so you take the standard square lattice, that's the graph, and then I will look at dimer covers of this graph. And more than that, I will look at a single type of domain in that square lattice. Okay, and that domain will be a square. Okay, that square can be placed on the square lattice in many different ways. In particular, two most straightforward ones is the first is when the sides of the square are parallel to the axis. And that's the left picture. And then on the right picture, I rotated the square by 45 degrees and, again, placed it on the lattice. I will actually mostly be interested in the picture on the right, and you'll quickly see why. It has a name in the mathematics literature. It's called Aztec diamond. It was named by Jim Propp, and the name stuck. And I think that's a rather pretty and appropriate name. So the problem is one starts with an Aztec diamond. One looks at all possible dimer covers, put them uniformly at random, and asks, what can you say about a random picture? Now, when you look at a picture like this, it's not really visually appealing. And you can't really see the features of the picture. So I will introduce 3 steps that will make the picture more transparent to our eyes, to our sort of naked vision without any computer enhancement. Okay, so the first step is that so the square lattice is a bipartite graph. All vertices can be colored white and black so that the edges go between white and black. And what that means is that the edges of the lattice can be split into 4 different types, not just 2, vertical and horizontal, but also vertical ones come in 2 sorts, those that have white on the bottom and those that have white on the top. And horizontal similarly comes in 2 types, right? So we have 4 different types of dimers in the square lattice. That's first. Now, the second convenient tool is to look at a domino tiling instead of the dimer cover. So around every edge that's covered by a dimer, I will draw a 2x1 rectangle, a domino tile, and place it there. Okay? And so that's an equivalent language, really. I can think about domino tilings of that domain on the right. Now, since my edges come in 4 different types, I can color the dominoes in 4 different colors, right? We're OK? Nothing wrong with that? So that would be a picture like that. And so finally, I'll come to the bottom row. And at the bottom row, there is a sample of a random dimer cover of this square, only much larger, and this square, only much larger. And I hope you do see that the 2 pictures are drastically different. When you look at the picture on the left, OK, you probably could agree that it's a random picture. And if you see the picture on the right for the first time, and somebody tells you, well, this is a picture drawn uniformly at random, then I think the natural feeling should be a surprise. It's not random. It shows features, right? And there is this pure color in every corner. There is this boundary that separates them. Something is going on. Maybe it's a mistake in the computer simulation. Well, it's not. It turns out that almost all dimer covers of that domain, or domino tilings, do give this picture. Before going further, let me introduce one more tool that will make pictures even more visual. Okay, so for that purpose, I'll go to the 3rd dimension. So far, all my pictures were flat. And I will now try to make them 3-dimensional. So what I will do is, so these are my 4 different dominoes. And I will turn them into 3-dimensional shapes in a particular fashion. Okay, and I hope that you see what's happening, right? So they're being lifted in space and sloped in 4 different directions. There are these gray attachments to it, but you'll see why this is convenient to do it. Okay? So once you do that, the advantage to it is that if you start with a domino covering of the Aztec, or any other domain for that matter, and if you turn each tile into this 3-dimensional shape, then this thing will turn into a graph of a continuous function. Well, pretty much. And so instead of just looking at this flat picture, we could look at this bird-like 3-dimensional feature. It's actually one-to-one. So if you know this function subject to certain conditions, it does give rise to a tiling. So it's just more convenient sometimes to speak about functions than to speak about tilings. Okay? And I think it's visually more appealing to look at the 3-dimensional picture. You might see more, right? So then this is the tiling picked uniformly at random for 200 by 200 Aztec diamond. And I can make it 3-dimensionally just as well. And if you do that, then you see that not only there is the separation of phases, there is pure and non-pure colors, but the whole 3-dimensional picture approximates some surface. And again, how come this is a uniformly at random, right? How does it know what that surface is? Right? And going back to the slide, well, actually not going back to the slide. So looking at the usual square, usual meaning the sides are parallel to the axis. If you do the same trick, you also get a 2-dimensional surface. And the 2-dimensional surface that you'll see will be drastically different. It will be roughly flat. Okay, so ignore these colored angles. They're just there to compare the picture to the previous one. But you see that there is a big difference between this picture and this picture. There is an honest, non-trivial plot of a function, and there is, well, okay, honest plot of a constant. Okay. All right. So this is the first. This function, the plot of which I'm looking at, is called the height function, and it exists in some level of generality. And when it exists, it makes it much easier and much more natural to talk about dimer covers. Right. So this is the uniformly at random picked dimer cover or domino tiling of the Aztec diamond. And mathematicians studied it for 30 years. And by now, almost any reasonable question you can ask has been answered. Okay? I could have easily given 1 or 2 lectures just focusing on different features of this picture. And one can look at the surface, what the surface is. One can take a microscope and zoom in at the edge of the picture and see what the fluctuations of the edge is. Well, actually, I didn't tell you what the separating curve is. The separating curve is actually the circle. Well, as the picture suggests, it's called the Arctic circle. There are other related models where the picture will suggest it's also a circle, and it will not be. But here, it's an honest Arctic circle. And then, actually, the first pretty fact is that the number of domino tilings of this domain is a pure power of 2. That's a very sort of nice fact. And there are other facts. There are connections to many different pieces of mathematics, to random matrix theory, to conformal geometry, and so on. And that's not what I really want to talk about. Okay? I want to add one feature to the model that will make it more geometric. So what is that feature? Instead of picking my domino covers or my domino tilings uniformly at random, I will bias them. So I will make some of them to appear more often, or they will be more likely, and at other ones will be less likely. How am I going to do that? Well, what I'm going to do is I'm going to assign a number, a weight, to every edge of the square lattice, a positive number. And then I will assign a weight to the whole dimer cover by multiplying the weights of the edges that are occupied by dimers, right? So, just multiply the numbers that are associated to the edges that are covered. And so then every dimer cover gets its weight, and they will not all be 1. They will be some numbers. And these will be proportional to the probabilities with which these covers appear. Okay? So if some weight of an edge is close to 0, then dimer covers that use this weight will have very low probability, and they will rarely appear. Okay? And I will assign these weights not so my domain will be large, and I will not assign the weights arbitrarily. That's too many parameters. What I will do is I will assign them periodically. So I will choose some fundamental domain in the lattice. So here is a k by L fundamental domain. And that fundamental domain, I'll choose in some way the weights. And then I will replicate them periodically, horizontally and vertically. That will give me weights on the whole lattice. And so then I will be able to compute the weight of a dimer cover on as large of an Aztec diamond as I want. Are we all right? So far, so good. So the next thing I'm going to do is I'm going to utilize this type of biasing, and I'm going to show you pictures of the random domino covers picked in this fashion, so with this probability distribution. And you can make your guess in your head as to how they would change from what you've seen before. Okay? So maybe first I'll show you a variety of it. So these are examples of what you get by choosing weights of the edges in some way. So this is a picture of, the resolution of the projector is making it a little bad in here. Okay. So let's see, what do we see? First we see, of course, that the circle disappears, okay? It turns into something strange, maybe something even with singularities, right? That's the first thing you mentioned, you notice. The second thing is that, they seem to appear, these curves seem to appear rather diverse. And then the other thing that you mentioned is that within the chaotic domain, there seems to be regions which are different from other regions. So the homogeneity of the picture sort of suffers. And so then you go into the three-dimensional picture. So this is an example of a 3x3 periodicity. And then you look at this region that looks a little bit strange, and you look three-dimensionally, and what you observe is three-dimensionally this region turns into a very flat piece. So this hyperbolite type shape that we saw for the uniform case changes and develops facets inside. That's a rather interesting phenomenon because you made a microscopic change. You placed bias on the edges microscopically, like maybe every third edge is more likely, or something like that. And then the global picture exhibits something new. It exhibits a new face, something you haven't seen before. So the fluctuations around here, as the Aztec diamond grows, will actually be of order 1. This is a really flat piece. I mean, I'll make an attempt to show it in the 3D simulation live, but on a laptop it's a little. So this is an example of a 2x2, and in the middle you see this strange region, right? I mean, it's visibly different. And so if you go in 3 dimensions, there we go. There is this flat thing. And if I try to zoom in, you see it's really flat. Right? So this is really a new phase from the point of view of statistical physics. The correlations are different. Everything is different. And so, so the microscopic, so the conclusion is that this biasing of the edges made some drastic change. So what's really happening? And so if you're about to fall asleep or start checking your email, so then the main message that I would like you to remember, if any, from this talk, is that when you look at the picture like this, where you see some messy thing with the pure corners and then these flat regions and something like that, so that thing is actually a Riemann surface in disguise. Okay? So this is, to me, a manifestation of how an easy setting of the problem leads to fairly deep mathematics that's required to describe it. So if you want to understand what this is, what exactly the curves are, how they are formed, then really what it is a certain map. So that takes this picture to this picture. Okay? And that's the upshot of my talk. So how does this map work? Well, you imagine a pretzel with 4 holes. There are 4 holes there, which corresponds to 4 flat regions here, which, well, there is 1, there is 2, there is 3, and there is 4. I'm not sure how well they're visible. And so that Riemann surface, so this surface is described by a polynomial equation, just a polynomial in 2 variables. I'll call it P. It lives in a 4-dimensional space. I can only draw a topological type. Drawing in 4 dimensions is beyond me. And then, in order for me to go from here to here, I need an intermediary object, which is pretty on its own right, I would say. That object is called an amoeba. I think one doesn't need to explain why it was called that. So the amoeba is the image of the Riemann surface under the log map. It's a pretty simple map. You take the logs of the absolute values of the 2 coordinates, and so that takes C2 to R2, and that takes the Riemann surface to the shaded part over here. Okay. Now, actually, this is not a one-to-one map. What happens is that the curve here has an involution, and so, well, just a complex conjugation, really. So there are 2 halves. So if you cut 1 half, then on the top half, on the bottom half, this will be a bijection. And the 4 holes are the 4 compact ovals that you see there. And then the 2 halves just sort of gets, so you can imagine actually this Riemann surface by taking 2 copies of this amoeba and just gluing them on the boundary. And topologically, you actually get this Riemann surface. Okay? And now this picture, okay, possibly you could see that it's already flat, so it's closer to what I want to describe. So from here to here, there is an explicit map, actually. There's an explicit diffeomorphism between this picture and this picture. So this is the description of what the limiting behavior of domino tilings of the Aztec is. For those who have a little bit more expertise with algebraic curves, there is also an associated picture of what's called the Newton polygon. So if you write this polynomial as a linear combination of monomials, then each monomial is z to the k w to the l. And so you can place all these points kl on the lattice, on the 2-dimensional lattice, and thus they will form a rectangle. In this case, it's going to be a square. And then there is a one-to-one correspondence between points of this rectangle, of the square, and the picture here, where, well, not really one-to-one, but well, almost one-to-one, where in order to get from here to here, you need to compute the gradient. And if you compute the gradient, well, so this whole flat piece, the gradient of the flat piece is the same for the whole flat piece, and so this will go to a single integer point within the square. And this corner maybe will go to this corner. So the corners will go to the corners, the flat pieces will go to the integer points, and on the rest it's going to be one-to-one. So there is a pretty good correspondence between the random picture and the Riemann surface picture. I guess the question is why? How does randomness on dimers know about complex analysis? Any questions? Yeah. How do I color?
What is the color in the amoeba or on the momentum on the polygon?
So the amoeba was not supposed to be colored. There is no color on the amoeba. On the next slide, there will be some. I'll explain. The coloring of the Aztec is just the coloring of the 4 types of the dominoes.
Okay, this is not associated to any other invariant on the polygon.
No, no. And here I just separated points of different types. So these are all integer points, corner points, boundary points, and integer points. I mean, there is, that's just right.
I think maybe the question is, how do you actually generate one of these random?
Right. So that is a very good question. So how do you actually generate a random sample of that measure? So there is a non-trivial answer to that question, and it's related to the specific domain. So for this specific domain, there is an algorithm called shuffling of dominoes, that allows one to produce an exact sample if you believe that your computer is capable of producing an independent sequence of zeros and ones. It's, if I had more time, I could actually show you in real time how the diamond grows, and it's an inductive procedure, and in one pass, you generate some. So in one pass, when the diamond is growing, there will be 2 by 2 squares that open up, and you can choose either this or this tiling of that square, and that's happening randomly with some weight. And in one pass, you generate a picture, and one proves that this is a perfect sample of the corresponding measure.
So you need a good definition of what it means to be random in this context.
Well, the definition of randomness I tried to give before. The definition of randomness is that the probability of a domino cover is proportional to the product of weights of the edges that it covers. This is the probability measure. And the question how one generates a random sample, well, that's a different question. And so in this case, we are lucky that there is an exact algorithm. In more general domains where there is no pretty algorithm, there are other algorithms that people run, Monte Carlo type, where you can still sample from the measure. You just need to run the algorithm for sufficiently long to see a reliable sample. But here, the samples that I'm showing are exact. I mean, they're very reliable, again, as long as you believe your computer is able to generate random numbers. Right. Anything else? Right. I went one step ahead. So one step ahead is that this map between, so I told you that there is a one-to-one map between the amoeba and the Aztec. And so that map, when you restrict it to the boundary of the amoeba, so now I do call it the boundary of the amoeba. It's also one-to-one on the boundary, so it maps the boundary of the amoeba to the boundary of the facets in the Aztec diamond. And so that map actually preserves the slope of the tangent line. That's a non-trivial feature, and it has a cute consequence. So that map preserves the slope, but it reverses the orientation of the boundary. And so on the amoeba, there are these compact ovals that are inside. And so when you go around it, you make a turn of 2 pi. And if you go around a corresponding hole here, well, you get minus 2 pi. And how can it be that you preserve the tangent line when you go around? Well, that can't happen. That can only happen if there are 4 points where the tangent line, or the direction of the tangent vector swaps. You need to compensate for 4 pi. And so that means there will be 4 cusps on every flat region that appears in the middle. And so even though it may not be extremely visible in this picture, but there is actually a 4 cusp thing sitting over here, and every flat region is 4 cusps. Okay? Sort of one nice geometric feature. Okay, so I'm going into the part where I'll try to explain why, even though you are completely random, you're still seeing a non-random surface showing up. What is the effect? How it appears, right? What's the mathematical or physical reason behind it, right? That's a rather general principle. One can look at other examples. So these are so-called lozenge tilings of the triangular lattice. And here, the 3-dimensional picture is pretty obvious to human eyes. And that's in 3D, and one looks at it, and there is, again, if you do it uniformly at random, there will be a surface that shows up. And the general principle is that whenever one considers a problem of this type that can be encoded by a height function, there is a variational problem whose solution delivers the limit shape for the corresponding height function. Okay? So there is it's somewhat similar, although not literally the same, to the minimal surfaces. If you want to know how the soap bubble looks, you need to solve a variational problem with the given boundary condition. So in order to see how the surface looks, you need to solve a variational problem with certain boundary conditions. The variational problem, though, is different than in the case of the soap bubble, and it depends on the weights of the edges. So we'll get to that. So why variational problem? Let me try to offer a quick explanation. So well, let's look at the limit shape. So what am I trying to do? So if your random surfaces, these stepped surfaces, exhibit a limit shape, that means that almost all of them look like that. So if you take any shape, any smooth function, any smooth graph, and you count how many different dimer covers give rise to plots that look like this. Okay, if you manage to count that, even approximately, then the maximum should be reached at the limit shape, right? Because that's where all of them live. So let's try to count how many dimer covers give rise to something in the neighborhood of a given surface, right? So how are we going to do that? Well, I'm going to take a surface, I'm going to cut it into pieces, which are small comparing to the global shape, but still large comparing to the lattice size. And then on each piece, I'm going to fix the boundary conditions, and they're going to be approximately flat, right? Because little pieces of a smooth surface are approximately flat. And then inside, I will allow the dimers to do whatever they want. But on the boundary, they need to glue to the neighboring piece just as they used to be glued again. So this way, I will be counting how many ways I have to fill each of these tiny squares, and then I can multiply all of these numbers over all squares, and that will be the approximate number of how many I have in the neighborhood, right? Okay. So then I'm down to the problem of counting the number of dimers in the flat neighborhood. So my boundary is flat, just like of the square. And I want to know how many tilings I have of the square. Except for the square might not be horizontal, it might be at the slope. But that's the same problem, essentially. This problem is exactly solvable. So this is a nice exercise in discrete Fourier analysis. And this is actually the answer for the actual square, for this square. So believe it or not, this product is an integer. You put it in a computer, and the computer will agree up to its precision that this is very close to an integer. A product of irrational complex numbers will produce an integer. OK, so you multiply these integers all over, and that's your functional. Well, actually, the log of it, right? Because rather than the product, you want this to sum something. So you get the integral over the surface of the log of this number. So the log of this number is called the free energy in physics, or surface tension in mathematics, because surface tension directly relates to the analogy to the minimal surfaces, to the soap bubbles. And so this surface tension can be computed, and was computed in a beautiful paper by Kenyon, Okunko, and Sheffield close to 20 years ago. Okay? And that's where the complex analysis comes in. So I said that this is a piece of discrete Fourier analysis, and indeed it is. So the way that one builds, or the way that one computes this functional, is that one takes the fundamental domain on which I assign the weights. So these are the weights on my lattice. And then I put additional weights for, you should imagine that this fundamental domain lives in a torus, right? Because after all, I'm replicating it up and down periodically, so it's really on a torus. And so then I take two generating cycles on the torus, and on these cycles, I place two complex variables. So on edges that intersect one cycle, I place z. On edges that intersect another cycle, I place w. And then I take the determinant of the size equal to the number of vertices here, and matrix elements are the weights of the edges corresponding to the two vertices, which are row and column. Okay? That will produce a polynomial in Z and W. And that's the polynomial that will give rise a little later to that Riemann surface that encodes the whole picture. Okay? So it's a pretty algorithmic thing. You could just compute it. Right, so the amoeba is the image of this thing under the log map. So that's the amoeba. And the surface tension can be computed through a formula. Okay, so there is a formula involving this, this polynomial. This is known as the Ronkin function. If you remember a complex analysis class, there is something called Jensen's formula there, where one counts zeros, or rather one counts the sum of logs of zeros of a holomorphic function by integrating the log of the function over a circle. Well, now the function is in two variables, and one integrates its log over two circles, over a torus. That's the analog of that in 2 dimensions. As the result, one gets a function that's convex over the shaded part, over the amoeba, and piecewise linear over the ovals, over the complement of the amoeba. Then the Legendre transform of that produces the surface tension, or the free energy. So that will be the functional of the slope that needs to be maximized. So the variational problem is that you have a surface, you integrate over a surface some function of the slope, and that function of the slope is this fairly complicated object.
I haven't understood your formula for P.
Yeah.
The determinant. How does this go?
So the formula, so under the determinant, there is a matrix with rows and columns parametrized by white and black vertices. And at the location that corresponds to a black vertex and the white vertex, you put the weight of the edge joining these 2 points. And if there is no weight, you put 0. That's the formula. Yeah, I skipped it. So thank you for keeping me honest.
So presumably the different weights account for the asymmetry in the picture of the amoeba. Is that right? The 4 holes are all different.
Well, I mean, all the information is held by this polynomial. So you can decipher it by putting the weights of the edges, or you can produce analytic information in this way. Okay, but
I guess my question was, is that picture of the amoeba, is that just a sketch, or is that a more or less exact rendering of what it looks like?
no, this is an exact picture. This one is not a sketch. This one is it appeared before, and that it was exactly the amoeba that corresponded to the tiling that was over there. So this one was honest. All right, so maximizing this functional is actually a difficult problem. Okay, so it gives you the understanding that the limit shape exists and unique because this is a convex functional, but it doesn't tell you how you compute it. And people don't know how to do it. In fact, until recently, for no domain, it was known how to do it for general periodicity. Aztec diamond is the only domain for which it is now known. So why is it known? There needs to be some extra ingredient that makes it solvable for the Aztec diamond. So that ingredient comes from partial differential equations, actually, completely integrable partial differential equations. And that's, again, the prettiness of the problem for me. Somehow it tells you what it wants to be solved, and it goes in different directions. So I'm not going to go too far into that. Let me tell you a problem that you can put on a linear algebra exercise sheet whenever you teach multiplication of matrices. Okay? So here it is. Take 2 matrices, 2 2x2 matrices like this. Alpha, beta, gamma, and delta, A, B, C, D are all numbers. Z is a variable. So there is a z here, and there is a 1 over z here. Okay? So you take the product of these two. Now, if you compute the determinant, then there will be a 0 of this determinant when z is equal to something. So z is equal to what? Alpha delta divided by beta gamma, right? And there will be a 0 of this determinant when z is equal to something else, right? Now, what I want to do, I want to refactor these matrices so that the zeros switch places, so that now this factor goes to the left, and this factor goes to the right, but the numbers changed so that the 0 got preserved. So I'm swapping the two matrices in such a way that the solution to the equation determinant equal to 0 remains the same. Okay? I'm refactoring two matrices, keeping the solution to z equal to 0, and swapping their places. Okay? So for 2 by 2 matrices, you just do it. This is the solution. So x here is this number, and if you substitute and you compute the 0 here, you see that it's the same as here, and here is here, and the product of the matrices here is equal to the product of the matrices there. Okay. All right. So now you take these two matrices, you take them by hand, you put them in the opposite order, and you refactor again. Put them in the opposite order, refactor again, and you do it 1,000,000 times. If you are able to control what happens after 1,000,000 iterations, you know what the limit shape of the Aztec diamond is for 2 by 2 biasing. I'm not telling you why. I'm just telling you what it boils down to, where the difficulty of the problem is. Okay? So how do you do it? This is a nonlinear map on alpha, beta, gamma, A, B, C, D. Iterating it 1,000,000 times, well, good luck with that. The computer dies pretty quickly. So there needs to be a tool of how one iterates maps like that. Okay? So what's here in red is actually the same thing. It says that you take the product to the power n, and you want to refactor it. This is called Wiener-Hopf factorization, a solution of the corresponding Riemann-Hilbert problem. So this technique is known from 1970s. This is called the finite gap method, and it was really developed for partial differential equations like this one. This is the KdV equation, Korteweg-de Vries equation for the shallow waves. But we don't need to go there. Let me try to tell you what the gist is, why you are able to. So the upshot is that you're able to linearize this flow. Right? So you have this flow which is nonlinear, and there is a change of coordinates that makes it linear. There is a smart change of coordinates that makes it linear. So what is that smart change of coordinates? Right? So you start with this matrix, right? This is my two matrices product, so this is your space on which the evolution lives. And your flow is permuting two matrices. Well, that's just conjugating by one of them, right? So you're really just conjugating. So when you conjugate the determinant doesn't change, but not only the determinant doesn't change, but the characteristic polynomial doesn't change either, right? Good, so that's very nice. That tells you that there are many first integrals, many conservation laws of the flow. The characteristic polynomial of the matrix doesn't change under that. So then, if one takes the characteristic polynomial, maybe I'll go to the next slide, actually. If one takes the characteristic polynomial, this is this one, and equates it to 0, this is where, well, the determinant equal to 0, so there is a null vector. So I'm looking for the eigenvector of my matrix, right? Eigenvector for the matrix P of Z with eigenvalue W. The coordinate that will linearize the flow is the singularity location of that eigenvalue. So my matrix will have, of that eigenvector, sorry, will have the eigenvector that I call Psi. It depends on Z and W. Z and W, they live on the algebraic curve. given by the equation that the characteristic polynomial vanishes, right? You know, that's literally the condition for the existence of the solution to this equation. And so then, this is a meromorphic function in Z and W. You look at where its singularities are located on the curve, and it will turn out that you know where all singularities are except for one. At each step of your flow, some easy considerations by just looking at degree of polynomials will determine where the singularities are except for one. But then there is a beautiful theorem in complex analysis called Abel theorem that tells you that if you know the positions of singularities on a compact Riemann surface, all but one, the final one, if the function is meromorphic, is uniquely determined. This is realized usually by something called Abel-Jacobi map. So one maps a Riemann surface to a torus, which is called the Jacobian of the Riemann surface, which records the integrals of one forms. And then the images in the torus of all the singularities need to all add up to 0. That's Abel's theorem. And so if you know many, but not one, then since they all add up to 0, you can figure out what that one is. And so that singularity, that unknown singularity, propagates on a torus along a straight line. And all that can be made effective with the use of theta functions, with the use of the special functions associated to the Riemann surface, and that makes it possible to eventually completely solve the flow. Okay. Now, I went a little fast. Literally, there is a half semester material under the finite gap method here. What I tried to say is that the key is in looking at what people would call in partial differential equation the wave function or the eigenvector of your object. And not just at it, but at its singularities. And the fact that you are dealing with meromorphic functions, the beauty of complex analysis, the rigidness of it, allows you to actually extract the unknown piece. All right, so I am on the finish line, essentially. I will mention that this procedure of taking two matrices, or just taking a matrix, factorizing it, and then taking the factors, placing them in the wrong order, refactoring, placing in the wrong order, refactoring, and so on. This is very well known in mathematics. In fact, computers use it millions, if not billions of times every day by computing eigenvalues. So the QR algorithm, a very widely used algorithm of numerical linear algebra, does exactly that. It factors the matrix into an orthogonal and upper triangular one, then places them in their own order, refactors, places, refactors, and so on. And that converges to an upper triangular matrix, which will have the eigenvalues on the diagonal. A stable, very well established algorithm. Now, slightly more geometrically, if one wants to compute the trajectories of billiards in an ellipsoid, like these pictures here, this is also a nonlinear map that was linearized by Jacobi, and that's where Jacobi theta functions showed up. So he was the first one to solve the problem, to introduce the special functions that solved it. And okay, he didn't formulate it in the matrix refactorization language, but that can be done. It's not difficult. So in some way, the linearization goes back almost 200 years. And then so the last one is maybe the least appealing of the three. That's the earlier equations of the rotations of a rigid body. If one wants to discretize them in such a way that they retain their integrability properties, then it's also doable with this matrix refactorization procedure. All right, so now I'm going to spend 2 minutes on telling you what I didn't tell you. So this is what these are the pictures I talked about in this talk, right? So these are my Riemann surfaces in disguise, right? So the Riemann surface, I do some weird thing to it, and it spits out the Daimler picture. Now, I never took a class in Riemann surfaces, and so when I deal with Riemann surfaces, there is, as usual, when you deal with something that you didn't learn as a young person, there is always some feeling of insecurity. Maybe you don't feel it the way you want to feel it. I was looking for ways to make this so that I could feel it better. These theta functions for surfaces of higher genus, they're complicated objects. Even computing them on a computer is not so easy. Okay, so imagine this. You have your weights of the edges, and you square them all. And then you redraw the picture. Or maybe you raise them to the power 10 or 100. So what happens if you raise these numbers to a power? Well, bigger numbers become even bigger, and smaller numbers become smaller, right? So this is, in some way, an analog of introducing a temperature to your system. If you're familiar with Gibbs measures, there is the standard form. The Gibbs measure is exponential of minus h, which is the energy, divided by the temperature, right? So temperature is like the inverse power that you are raising the weight to, right? So if you do that, this is what happens. So this is when all weights are raised to the power 0. That's the uniform measure, all ones. That's we know, that's the Arctic Circle. And then as you lower the temperature, this is what you see in the end. There are no curvy parts that show up. There is just a crystal. The height function becomes piecewise linear, but in a non-trivial fashion. You see there are obviously some polygons inside, and something like, there is still structure remaining. So this is the analogy. Remember my first picture that I had of the helium, right? This is the absolute zero. This is the crystal. And remarkably, to me, the Riemann surface degenerates, but not to a triviality, to something called tropical curve. So there is a whole subject called tropical geometry, and I find it very convenient. Everybody knows that tropics arise when the temperature goes to 0, right? So the tropical geometry is the thing that describes this crystal in a way that's parallel to how the complex geometry of the Riemann surface describes this curved picture. And even though this is a simple and degenerate picture, I personally derived some satisfaction to it, because now I can draw this, no problem. I just make my computer solve Kirchhoff equations. Kirchhoff equations for the harmonic function of discrete graph. Everything is linearly algebraic. Everything becomes tame, but still non-trivial. So the number of flat regions here is exactly the number of crystal faces here, and so on. And so that helped me to make peace with the complexity of that picture somehow. All right, so I like to make a summary page at the end of the talk, and I was never a geometer. Actually, I'm quite incapable in geometry. And I realized that for the first time in my life, I'm able to write a summary without words, just with pictures. And I couldn't resist. So thank you very much for listening.
Well, thank you for a beautiful and I think somewhat mischievous talk. There is time for some questions, and I'm looking for questioners. Oh, wait.
Thank you. Thanks a lot, Alexei. So when you take this final limit that you took, it was like high temperature, right? Yeah. So are there new local quantities arising, like some new scaling limits arising as well? Local scaling limits, I mean.
Local scaling limits. So the local scaling limits in this picture were actually predicted in that work by Kenyon, Kunkov, and Sheffield, because they consider tiling, well, not only they computed the surface tension, but the way they computed it, they analyzed the picture on the torus, and on a large torus made out of the lattice. And so all possible limits of the tiling problem on the torus were computed in that paper, and so in the limit, so whatever you get on the torus is going to be translation invariant, right? Because torus is, well, has these symmetries, has the shifts, and so different tori will produce in the limit of large tori measures on the whole plane that are translation invariant, and they are the local measures that appear at different points of the Aztec diamond. So the local statistics have been predicted in a way more than 20 years ago. Now, if you ask questions about the edge statistics and so on, one would expect them to follow standard random matrix laws, but that hasn't really been checked. Am I answering the question?
Yeah, but I mean also in the zero temperature limit.
Oh, in zero temperature?
In the zero temperature limit, do the local limits remain the same?
No. No. So in zero, sorry, I missed the question. In zero temperature limit, imagine that. Imagine you have a finite domain, and every configuration has a weight, and now you start raising these weights to a power. As the power gets big, the configuration that has the highest weight will win. So typically for a finite domain, you will just have one configuration that dominates everything. That's the freezing. And so generically what happens is that in every region over here, there is only one frozen pattern, the one that maximizes the energy for that particular slope. So there is no randomness remaining in this picture even locally, generically. But non-generically, we don't know exactly what happens, because you can have pictures which will have features both of the tropical world and non-tropical world. There could be parts of this picture that are melted, and other parts will be tropical. There could be pictures where you have more than one maximizer locally, and then how do they combine it? So this is the generic picture that I told you about, but the non-generic picture, when you have some non-trivial algebraic relations on your weights, there should be some hierarchy of what's happening, and that's not done. So there's a pretty rich world over there.
Yeah, thank you.
Thank you for the talk. So with weights in the Aztec diamond, you see the rectangle. If you start with the rectangle and you put weights, do you see some difference in patterns?
You want to take a rectangular domain and play the same game. That's what you're saying. Well, depends on how you place the rectangle. If your axes are parallel to the coordinate axis, I don't think you're going to see anything interesting. You're going to see sort of a flat. And it's easier not easier, but it's more productive to think in terms of the boundary condition on the height function. Because for the Aztec, you impose the height function that goes up, and down. Sort of the most non-flat boundary condition you can achieve without destroying dimers altogether. Okay? For the square with the parallel axis to with the sides parallel to the axis, you give the boundary condition that's just flat. Well, and you're going to read off the solution that's just flat. So if you give some boundary condition that's neither this or that, Well, the abstract theorem was going to tell you that there is a limit shape. But there is no theorem that's going to tell you what it is. I mean, it's a maximizer of the functional. And as I said, there are at present no domains other than Aztec for which the answer is known. So, and in the hexagonal lattice, there is now an answer known for maybe conjecturally or partly conjecturally for the hexagon. But that's it. And not even for general periodicity. For general periodicity, Aztec is really the only example that so far is solved.
Okay, I think we have time for one more question, and then it's coffee break.
Thank you very much for the talk. What's a gentle introduction to this mischief? I mean, so like a nice little thing we can read. I know there are so many connections. What do you suggest?
You want an introductory text, right?
Yeah, something.
Yeah, lectures on Dymo models, I think that's called. There is a nice book which came out of a lecture course by Vadim Gorin, published by Cambridge University Press, and you'll find references there. I mean, it was written before the progress that was achieved with these, with the flat regions, but it will certainly be enough of an introduction. So I can recommend it. I think it's a good book.
Very good. Okay, so again, thank you very much. And,
Thank you.